Dimensional accuracy is determined by tolerance. Different in size tolerances for sizes up to 500 millimeters are found by formula T is equal A multiplied by E, or I. A multiply I, where I is a unit of tolerance. I is a unit of tolerance, which expresses the dependence of the tolerance on the size in micrometers. I is a unit of tolerance which expresses the dependence of the tolerance on the size in micrometers. And I is calculated by this formula. Use this formula to calculate I. In this formula, D suffix M is the geometric mean of the limit values of the interval of nominal dimensions. It is calculated by the formula. Use this formula to calculate D suffix M. We use D suffix minimum and D suffix maximum. Where D suffix minimum and D suffix maximum are smallest and largest limit values of the interval of nominal dimensions in millimeters. Smallest and largest limit values of the interval of nominal dimensions in millimeters. What is the minimum and D maximum? We use these tables. These tables or these tables. For example, we have a hole or shaft, and diameter, nominal diameter of the hole and of the shaft is equal 60 millimeters. 60 millimeters is between its basic size diameter steps in millimeters. 60 millimeters is between 50 millimeters and 80 millimeters. We use this interval to calculate D suffix M. D suffix minimum, D minimum is equal 50 millimeters and D maximum is equal 80 millimeters. We use formula to calculate dm, 50 multiplied by 80, and we calculate d suffix m, and we use this parameter in the formula to calculate I, the unit of tolerance. We use dm and we find I, the unit of tolerance. It's the first part of the formula to calculate T, tolerance field. And what is the A? A, the number of units of tolerance. I, unit of tolerance. A, the number of units of tolerance. We use these tables to find the number of units of tolerance A. This row is A. For each IT grade, we can find A. For example, for IT grade IT8, A is equal 25. For IT grade 12, IT12, A is equal 160. For IT grade IT9, A is equal 40. So we can find unit of tolerance I, and we can find the number of units A. If we know I and A, we can calculate T, the tolerance of the tolerance field of the size. Have you questions?
No, teacher, till now, no.
Okay, next slide. Next slide. Within one IT grade, A is a constant. If we look to the table, we can see that for one IT grade, for example, for IT5, A is constant. A is equal 7. For different dimensions, dimension is changed, IT grade is constant, and A is constant too. For another IT grade, A will be another value, will have another value. For example, IT7, A is equal 16. Within one IT grade, A is a constant. However, the tolerances in the same IT grade for different sizes change, because with increasing size increases the unit of tolerance. Unit of tolerance, it's I, and I is different for different sizes. And we calculate I, and we use diameter, D suffix M. In the transition of coarse precision IT grades, the tolerances increase due to the increase in the number of tolerance units. In ISO, for sizes up to 10,000 millimeters, 19 IT grades are established. Please write down these sentences. In ISO or ISO, for sizes up to 10,000 millimeters, 19 IT grades are established. In order of decreasing accuracy, IT grades tolerances are conditionally indicated. IT01, IT0, IT1, IT2, IT3, and the last IT17. And if we calculate all of these parameters, we will have 19 IT grades, because IT01, IT0, and next IT1. From IT1 to IT17, it's 17 IT grades, plus 1, 18, and 19 IT grades. in sum, we have 19 IT grades. IT 01, IT 0, and IT 17. IT grades is international tolerance grades. This row is different IT grades. IT 01, IT 0, IT 1, IT 2, IT 3. If we use our table, we can see the IT grades too. IT grade 01, IT grade 0, IT grade 1, 2, 3, 4, 5, 6, 7, and 17. In this table, IT grades is IT 16, in this table, IT 18, but now we have IT 17, the largest IT grade, IT 17. These are the standard tolerance grades. These tolerance values will be calculated with the help of the relevant magnitude given below. A is equal 7 for IT grade 5. A is equal 10 for IT grade 6. For IT grade 10, A is equal 64. And I, it's unit of tolerance. I, it's unit of tolerance. A, the number of units of tolerance. Please write down this table in your notes, and we use this table in our practical lessons.
Yeah, okay, teacher.
We use IT grades from 01 to 4 for the production of gauges, plug gauges, measuring instruments. From IT 5 to IT 7 for feats in precision engineering applications. From IT grade 8 to IT grade 11 for general engineering. For example, when we use in general engineering, we use IT grades from 8 to 11. From IT grade 12 to IT grade 14 for sheet metal working or press working. For IT grade 15 to IT grade 16 for processes like casting, general cutting work. It's for work pieces. We use these IT grades when we made work pieces. And its fundamental tolerances of grades from IT 0, 1 and to IT 16 according to IS 9 ISO 919. We will use this table in our practical lesson. And for example, tolerance field for the shaft with dimension, with nominal dimension 35 millimeters, and IT grade 10. We use this row, and 35 millimeters is between 30 and 50 millimeters. This row, and IT grade 10, and we have tolerance field is equal 100 micrometers. 100 micrometers. For example, shaft, it was shaft, a hole with nominal dimension, nominal diameter of the hole, 115 millimeters. 115 is between 80 and 120. We use this row, IT grade 11, IT 11, and IT 11, and we have tolerance field is equal to 220 micrometers. It's standard tolerance grades. Standard tolerance grades. And we use this formula to when we calculate the tolerance field. Example, calculate the standard tolerance value. Question, calculate the value of standard tolerance IT7 of diameter 100 millimeters of the shaft. 100 millimeters of the shaft. Step 1. Calculate the geometrical mean D suffix M. The shaft diameter 100 is between 80 and 120. D maximum it's 120, D minimum it's 80 millimeters. D maximum 120, D minimum is 80 millimeters. And what we will have, the shaft diameter 100 lines in the nominal size range 18 to 120 millimeters, and the geometrical mean D is 98 millimeters. Step 2. Calculate standard tolerance factor I. We use another formula. This formula we use D suffix M, and we find I. I is equal 2.172 micrometers. And step 3, calculate the value of tolerance IT7. For IT7, we must find A, number of tolerance units. We use this table. For IT7, A is equal 16. For IT7, A is equal 16. 16 multiplied by I, 16 multiplied by 2.172, and we have 35 micrometers. Its tolerance field for IT7, 35 micrometers and diameter 100 millimeters of the shaft. Can we start another item, 3.2?
Yes, teacher, please.
Okay. 3.2, fundamental deviations, diagrams of the location of the fundamental deviations of the shafts and holes. 3.2, fundamental deviations, diagrams of the location of the fundamental deviations of the shafts and holes. A number of tolerances of 19 IT grades and 28 fundamental deviations of the tolerance fields of shafts and holes have been established for the formation of tolerance fields for each interval of nominal dimensions. The fundamental deviations of the deviations are denoted by 1 or 2 letters of the Latin alphabet, like in figure 3.1. A, B, C, D, it's a Latin alphabet, letters of Latin alphabets, and its fundamental deviation, A, B, C, D, E, F, F, G, J, H, J, K, M, N, P, no, and another letters. It's 28 fundamental deviations. It's zero line or basic size, zero line, and tolerance fields. Fundamental deviations letter for hole basis and fundamental deviation letter for shaft basis. If we use big letters for hole and small letters for shaft. A, big A, it's fundamental deviation for hole, and small a, it's fundamental deviation for shaft. Big R is fundamental deviation for hole, small r is fundamental deviation for shaft. Basic size, fundamental deviation for shafts because it's small letters, and fundamental deviations for holes because it's big letters of Latin alphabet. The fundamental deviation is that limit deviation which defines that limit of size which is the nearest to the nominal size. It's zero line and nominal size. We have tolerance field and the fundamental, and we have two deviation, upper limit deviation and lower limit deviation. The fundamental deviation is the z deviation which defines that limit of size which is the nearest to the nominal size. The nearest to the nominal size, it's for this tolerance field, it's lower limit deviation. So it's the fundamental deviation For this, for example, these tolerance fields. Fundamental deviation V. Upper limit deviation, lower limit deviation. The nearest to the nominal size, it's upper limit deviation. This dimension is lower than that dimension. So the upper limit deviation, it's the fundamental deviation for these tolerance fields. For the shaft, the same situation. Fundamental tolerance field and fundamental deviation C. Upper limit deviation, lower limit deviation. The nearest to the nominal size is upper limit deviation, and it's a fundamental deviation. For this tolerance field X, it's fundamental deviation. Upper limit deviation, lower limit deviation, and the nearest to the nominal size, it's lower limit deviation. So lower limit deviation, it's the fundamental deviation, and it's equal X. Its name, not equal, its name X for these tolerance fields. The fundamental deviation are identified and controlled by uppercase letters for holes, uppercase letters for big letters, A from A to ZC. Holes deviations, A, B, C, D, and another. Z, ZA, ZB, ZC. Lowercase letters for shafts. Small letters, it's for shafts. From A to ZC too, but we use small letters, lowercase letters. Shaft deviations, the same deviations, but we use small letters. A, B, C, D, ZA, ZB, ZC. And now we have a break for 5 minutes, and we continue our lesson after the break.
Okay, teacher. Okay, teacher.
So the next slide. The fundamental deviations of the holes should allow the formation of fits in the hole system and in the shaft system, which equal clearances and interferences. To do this, there are two rules for calculating of the deviations of the holes, general and special. According to the general rule, the fundamental deviations of the holes are taken equal in absolute value and opposite in sign to the fundamental deviation of the shafts, denotes by the same letters. Please write down the general and special rules. For holes with the fundamental deviation from A to H, big E is equal minus small es. It's general rule. For holes with a fundamental deviation from A to H, big E is equal minus small es. For holes with the fundamental deviation from I to ZC, big Es is equal minus small e. it was general rule and special rule. An exceptions to this rule is made for deviation of holes larger than 3 millimeters, JKM and N, JKM N, with tolerance to IT8, inclusive, and deviations from P to ZC to IT grade 7 inclusive. A special rule has been established for them. Big ES is equal minus small e plus delta. Special rules has been established for them. Big ES is equal minus small e plus delta. It's for fundamental deviations J, K, M, N with tolerance to IT8 and from P to ZC with IT grades to 7 IT grades inclusive. Where delta is equal IT suffix N minus IT grade suffix N minus 1. The difference between the tolerance of the considered IT grades and the tolerance of the nearest accurate IT grades. This difference is delta. And now I want to show to you some videos about fundamental deviations. Fundamental deviations. Video 3.1.
Hello friends, today we will learn deviation, lower deviation, upper deviation and fundamental deviation. Lower deviation and upper deviation. Deviation means the amount by which the dimension goes away from the zero line. Now in this figure you can see zero line, lower limit and upper limit, which we have studied in previous video. Lower deviation. The amount by which lower limit deviates from zero line is known as lower deviation. And upper deviation, the amount by which upper limit deviates from zero line is known as upper deviation. Fundamental deviation. It is either upper deviation or lower deviation, which is conventionally chosen to define the position of tolerance zone in relation to the zero line. It defines location of tolerance zone with respect to the zero line. Suppose, as shown in figure, upper deviation chosen as fundamental deviation, then its position will not change with respect to the zero line. Case 1. To increase the tolerance zone, only lower deviation will be allowed to move down in order to increase tolerance zone. Case 2. To decrease the tolerance zone, only lower deviation will be allowed to move up in order to decrease tolerance zone. So you can see in this figure, upper deviation is constant in both the cases, but lower deviation is varying as per requirement. So position of fundamental deviation is fixed with respect to the zero line in both the cases. Types of fundamental deviation. There are 25 types of fundamental deviation and these are indicated by letter symbols. Fundamental deviations for holes. These are represented by the capital letters. and excluded letters are I, L, O, Q, and W. Fundamental deviation for shafts are represented by small case letters, and excluded letters are again I, L, O, Q, and W. We will learn this topic in detail with IS system of limits and fields. If you like this video, don't forget to hit like button.
It was the first video, and let's look the second video.
I've wanted to make this video for a while. It's on something I've found very useful over the years, and I hope you will too. The ISO system of limits and fits. Contrary to most of the other videos on the topic, I'll be presenting this with a working microphone. If you've seen as many videos online as I have about this, you'll get that joke. Before I get too far into this, I want to say that this is my understanding of the ISO limits and fit system, and I did do my due diligence to make sure it was correct. But if I make a mistake, please let me know in the comments so I can either add edits to the description or, if I'm way off base, remake the video. So starting off, any dimension in existence has some tolerance to it. The tolerance specifies how much higher or lower a dimension can be from nominal and still be acceptable. The space between the upper and lower limit is often called the tolerance zone. Think about it like football uprights. Each upright represents a limit, upper or lower. To score a field goal, we kick the ball towards the center, but no matter how the ball flies, as long as it ends up between the uprights, it's acceptable, and our parents will still love us. Before we get any further, I should mention that I'll be talking about shafts and pins fitting in holes, but per ISO 286, this system can be used for internal and external features of size. You'll sometimes see it used for keys fitting in keyways, for example. How things fit together is determined by how much free space there is between the two parts. If there's lots, there'll be lots of space for the parts to move. If there's only a little, there'll be a lot less space. Finally, if there's no space, the part won't be able to move. In this video, I'll show the hole tolerance zone as red, and the shaft tolerance zone is green. This means that without measuring, the actual outer diameter of the shaft will end up somewhere in the green zone, and the actual diameter of the hole will end up somewhere in the red zone. A pin can fit into a hole one of three different ways: clearance, transition, and interference. A clearance fit means that there will always be space between the two parts, no matter how the tolerances turn out. Transition fit means there's sometimes space between the parts and sometimes there isn't, but it's usually pretty close. Interference fits never have space between the parts, and one part always has to be forced into the other. It turns out these categories can actually be quite broad. For example, a 9mm pin fitting into a 10mm hole is a clearance fit, but it would be extremely loose. A 9.98mm pin in a 10mm hole is also a clearance fit, but it's much tighter. The former might be good just to make sure two parts don't hit each other, and the latter might be good for making sure the pin stays approximately in the same position relative to the hole. Different fits, as well as their descriptions, can be found by looking up preferred fits and tolerances in the Machiner's Handbook. There's a preferred fit for most situations, and this is a really good starting point. Also, check out the YouTube video by Tarka on the ANSI system of fits and tolerances. The designations are different, but the concepts and considerations are the same. So if we want a dowel pin to fit loosely in a hole, we measure it, we ream the hole to have a little extra space in it, and we put it in. The problem arises when you have a bag of 100 dowel pins and you have to ream 100 holes. Dowel pins have a tolerance on them, and their sizes will always vary a bit. Your reamer will also cut slightly different sized holes, depending on your work holding, wear in the reamer, and the cutting parameters, all of which can change while reaming your 100 holes. Because you bought the dowel pins and have no control over their tolerance, this is called a shaft basis fit. So the challenge is now to decide what size reamer to use to make sure that all the dowel pins fit properly. If you know the tolerance range you can expect from your reamer, and you know the tolerances of the dowel pins, you can choose a reamer size where the smallest hole the reamer can cut still has space for the largest dowel pin. This is called the allowance, and is typically something you choose. You're allowing, say, 25 microns of space between the largest dowel pin and the smallest reamed hole. Because there will be other smaller pins, and your reamer will sometimes cut larger holes, you may also find yourself cutting the largest possible hole for the smallest possible pin. The extra space on top of the allowance is called the clearance. If the clearance is too large, the fit might not work. The only way to change the clearance without changing the allowance is to tighten up your tolerance zones, either by changing your manufacturing methods or buying tighter tolerance pins. Conveying tolerance zones can be a bit annoying. Say you own a factory that makes dowel pins. You want to be able to tell customers what the tolerance zone is on each size of dowel pin, but it would be cumbersome to have to create engineering drawings for each size. So instead, you can just say that tolerance will always be a bit over the specified dimension, where a bit over scales roughly proportionally to the target size. We could say that all the pins will be between 0.1 and 0.3% larger than the nominal dimension. The problem is we don't want people to have to constantly calculate what these percentages are. The system we use instead is called the ISO 286-2 standard. ISO 286-2 uses numbers and letters to convey tolerance zones, things like M6 and H7. The number, also known as the international tolerance grade, roughly indicates how large the tolerance zone is, and the letter indicates roughly where it is. The letter H always means that the specified tolerance zone includes the nominal size as one of the limits, and it diverges into the material. For holes, H means the smallest the hole can be is the nominal size, but it's allowed to be larger. For shafts, H means the largest the shaft can be is the nominal size, and it can only be smaller. The H tolerance zone is important because it's taken as the middle. Shafts or pins with tolerance zones before H in the alphabet will never be the nominal size. Holes will always be larger and shafts will always be smaller. After H, there are a few tolerance zones, such as J and JS, where the shaft can be larger or smaller, but as you go further through the alphabet, the shafts will get larger and larger and the holes will get smaller and smaller. Holes always get an uppercase letter and shafts always get a lowercase letter. Okay, so now we have a naming scheme for tolerance zones. For a given fit, we will usually have one component driving the other one's required tolerance zone. In this example, where we bought the dowel pins, we have no input on their tolerance, so it's a shaft basis fit. If we're designing a shaft that has to fit in a purchased bushing, we can't control the tolerance of the bushing, so we have a hole basis fit. Shaft or hole basis fits often use an H tolerance zone, respectively, since the H tolerance zone contains the nominal size as one of the limits. If we're lucky enough to be designing both parts, we do have some discretion, but you would normally base your fit on whatever side of the fit is harder to change. The preference tends to be designing for a hole basis fit, as in general, there tend to be more options for precisely reducing the diameter of a shaft than precisely expanding a hole. So what does a fit look like in the ISO system? It's simply the two tolerance zones specified next to each other. An H7G6 fit means, for example, the hole has an H7 tolerance and the shaft has a G6 tolerance. I've cut some holes in this piece of aluminum to show some examples of different fits. This is an undersized H6 tolerance dowel pin. The E7H6 and F7H6 are reasonably loose clearance holes. You can rattle the 12.7mm H6 dowels around a little bit, and they basically drop right through. The H7H6 and G7H6 are much closer fits, and can perhaps be used to locate parts while remaining removable. The JS7H6 is a transition fit that, as you can see, ended up being on the light interference side, but a rubber mallet would work to tap the pin in for a semi-permanent joint. Finally, the P7H7 is an interference fit and would probably require a hydraulic press, or at least a beefy arbor press to install. This might be a good time to point out that, contrary to my labels in my past example, individual holes and shafts can't be called JF7 or H7. The JS7 refers to the tolerance zone that the hole falls in. A hole that is 10.001 millimeters is in the JS7 tolerance zone, but it's also in the H6, H5, and JS5 tolerance zones. You have to remember that we can't measure the hole until after it's cut, and we have to specify the acceptable tolerance zone before it's cut. The fits also have some range to them. For example, these three holes are in the H7 tolerance zone, and these are three H6 dowels. Note how they fall through the holes at different speeds due to the minute differences in the clearance. The numbers themselves are actually determined by the IT system, the International Tolerance System. Every manufacturing process can be statistically analyzed and an IT number can be determined. This means that if I'm reaming a hole, I can look up the reaming process and see that at best I can achieve about an IT7. So I can't specify an H5 or a G5 hole if it's going to be reamed. Likewise, if you have to design something to fit inside a drilled hole, even if you don't have the tolerance for the hole in front of you, you can look up drilling and see that it has at best about IT10. So the whole basis for the fit is going to be around H10. So why would you use this system? Personally, I like how much information is available through just 2 digits. If I have to make a bearing seat on a shaft for an 8mm bearing, I can simply look up what tolerance is required from Machiner's Handbook or something similar. If I need a bearing seat for an 8mm bearing on a shaft that will see reasonably high loads, I can see that it recommends a JS5 fit. Machinists are not going to be happy about that. I know from the fact that it's JS, it'll probably be a transition fit and might need a little force to install, and the 5 tells me I'll need an IT5 process to make it, which will either involve very accurate turning or cylindrical grinding. As another example, if I want a nice sliding fit and the shaft I require will be in the H6 tolerance zone, I can simply specify a G7 on the hole tolerance without having to estimate how much allowance or clearance I want. Specifying a tolerance zone like this on a drawing does mean that the machinist might have to look up the actual numbers, so typically I include the fit as well as the tolerances. So knowing the different tolerance zones and having a list of a dozen or so preferred fits, we should be able to design parts that fit together how we want. We also have a means of vaguely checking if a manufacturing method will be capable of hitting those tolerances. In addition to the oft-used pin and hole example, the system can be used for internal and external parallel faces, such as keys and keyways, or other features of size. Well, that was a bit of a dry one, but hopefully you found it useful.
We return to our lection. And next slide. Hidden 3.3 hole system and shaft system. Location scheme of tolerance fields for fits. Fits of all these groups with different clearances and interferences can be obtained by changing the position of the tolerance fields of the two parts being connected. However, it is more convenient in technological and operational terms to obtain a variety of fits by changing the position of the tolerance field of only the shaft or only the hole. The part in which the tolerance field is not allowed to fall due to the type of fit is called the main part of the system. Please write down a main part of the system, the part in which the tolerance field is not allowed to fall due to the type of fit in ISO. The main parts are holes or shafts with a fundamental deviation of 0. Fundamental deviation of these parts is 0. It can be hole and it can be shaft, but its fundamental deviation is equal to 0. Then it's the main part of the system. Types of fit. There are two basic systems for giving tolerance: the hole-based system and the shaft-based system. The hole-based system and the shaft-based system. The main part is the part whose tolerance field is the basis for the formation of fits. Fits in the whole system, like in this figure, whole basis system. Fits in the whole system are fits in which clearances and interferences are formed by changing the limiting dimension of the shaft. The tolerance field of the hole is constant, and we change location and limiting dimension of the shaft. This is tolerance field of the shaft 1, tolerance field of the shaft, and this is tolerance field of the shaft 2. So if we use this field, we have clearance field. If we use this field, we have interference field. If the tolerance fields are crossed with tolerance field of the hole, it's transition fit. So fits in the whole system are feeds in which clearances and interferences are formed by changing the limiting dimensions of the shaft. Tolerance field of the hole is constant. And fundamental deviation of the hole is equal 0. This is 0 line. And for the hole, its lower limit deviation is equal 0. And it's a fundamental deviation too. Fits in the shaft system. In the scheme in figure 3.2b, shaft-based system. Fits in the shaft system are fits in which the necessary clearances and interferences are formed by changing the limiting dimensions of the hole. The tolerance field of the shaft is constant, and we change the tolerance field of the hole. Tolerance field of the shaft is constant, and we change tolerance fields of the holes. It's for the clearance fit. For the interference fit, we use this tolerance fields of the hole, and if we use one of these tolerance fields, we have transitions fit. Clearances and interferences are formed by changing the limiting dimension of the hole. In the shaft system fits. The hole base system. Hole bases lower deviation is 0. Its fundamental deviation is h. If we take this scheme, we find the fundamental deviation of the shaft h small h and the fundamental deviation of the hole big H, big H, big H. This is tolerance field, and we have the fundamental deviation of the hole and of the shaft is equal 0. If we have H, its fundamental deviation is equal 0 because it's 0 line and it's 0 line, and fundamental deviation H is equal 0. And we change the dimensions of the shaft in a hole basis. We change the dimension of the shaft, and we have positive allowance, 0 allowance, and negative allowance. It's clearance fit, transition fit, and interference fit. We change the dimensions of the shaft in the hole basis. In the shaft basis system, we change the dimensions of the hole, and basic size of the shaft is constant. Shaft basis, upper deviation is 0, and fundamental deviation is h, small h for the shaft, and upper deviation is 0 for the shaft. Hole 1, positive allowance, 0 allowance, and negative allowance. And we have clearance fit, and we have transition fit, and we have interference fit. We change only the dimension of the hole in the shaft basis system. In the shaft-based system. Limit deviations are assigned to all dimensions indicated on the working drawings. The accuracy of smooth elements for which deviations are specified by a common record in nominalized either by IT grades from IT 12 to IT 17 for sizes from 1 to 10,000 millimeters, or by accuracy classes, accurate, medium, rogue, and very rogue, denoted by the letter T. Accuracy classes are conditionally named and denoted accurate T suffix 1, medium T suffix 2, rogue T suffix 3, and very rogue T suffix 4. In the lesson accuracy classes, the limit deviations are set for the enlarged intervals, for example, from 6 to 30, from 30 to 120, and obtained by roundings of the average tolerance calculated according to the tolerances adopted respectively in IT grades 12, 14, 16, and 17 for the size intervals included in this enlarged interval. For the sizes of the metal details processed by cutting, IT grade 14 and accuracy class T suffix 2 are preferred. And in this figure 3.3, designation of limit deviation and fits in the drawings. We use three variants of designation of the dimension. We can use nominal diameter, fundamental deviation, and IT grade. It's a first variant. First variant, designation of diameter of the shaft, diameter of the hole, nominal diameter, fundamental deviation, J suffix S, and IT grade 7. And it's fit shaft with a hole in the another part. Nominal diameter. Above the line, the parameters for the shaft. Under the line, for the hole, big letters. We use big letters. And under the line, the parameters of the shaft. We use small letters. And we use fundamental deviation and IT grade of the hole, fundamental deviation of the shaft, and IT grade of the shaft. Another variant of designation of limit deviation and fits in the drawings, we use only limit deviations, nominal diameter and limit deviation, upper limit deviation and lower limit deviation. It's dimension of the hole of the shaft, dimension of the hole, upper limit deviation plus 0.006 and lower limit deviation minus 0.006. And the designation of fits, fit. Nominal diameter above the line, upper limit deviation and lower limit deviation of the hole, and under the line, upper limit deviation and lower limit deviation of the shaft. And the third designation of the dimension, we use the both variant. We use fundamental deviation and IT grade, and we use limit deviations. For example, for the shaft, nominal diameter 3.2, fundamental deviation RH, IT grade 6, upper limit deviation -0 or +0, it's equal, just 0. And lower limit deviation -0.008. For the whole fundament, we use nominal diameter 3.2 millimeters, fundamental deviation J suffix S, IT grade 7, and upper limit deviation +0.006, lower limit deviation -0.006. And designation of the feet shaft with the hole. Nominal diameter 3.2, above the line, fundamental deviation J suffix S, IT grade 7, above the line, upper limit deviation +0.006 and lower limit deviation -0.006. It's for hole. And for shaft, fundamental deviation H, IT grade 6, upper limit deviation 0, lower limit deviation -0.008. It was 3 variants of designation of limit deviations and feeds in the drawings. And now we have the time to look another video. We have 10 minutes, so we can look a video about hole and shaft based systems.
Previously on Mech Minutes Shafting Series, we covered primary considerations when selecting material and surface treatments. All past videos are posted for your reference to get caught up to this week's episode of Tolerances and Fits. A tolerance is the allowable amount of variation from a specified dimension. When tolerances are combined between a shaft and bore, they can be classified into 3 categories known as fits. The clearance fit, interference fit, and transition fit can either assist in assembly or prevent them from being disassembled easily. A clearance fit ensures a shaft can be freely inserted into the intended bore. This generally means the maximum limit of the shaft is less than the minimum limit of the bore diameter. An interference fit guarantees the shaft and bore will interfere at every point within their tolerance zone. This is commonly referred to as a press fit. Often the 2 components must be joined by excessive force or by altering the atmospheric temperature to slightly expand or shrink the diameter for assembly. The transition fit is a combination between the clearance and interference fit. Depending on the actual dimension of the shaft and bore, it is possible that either could occur. This fit is best used when a shaft must be held in a precise location. If interference should occur, it will not be to the extent where disassembly is overly difficult. Masumi shafts and bores follow the JIS shaft fit tolerances. Selecting the proper tolerance is critical to achieve the desired fit between 2 mating components. This tolerance table can be found in the technical reference section in each catalog. The columns represent the tolerance grade, while the rows are organized by diameter ranges. Finding where the 2 intersect will indicate the corresponding tolerance range. If we look at a 10 millimeter shaft with an H6 tolerance, 10H6, we can see the expected tolerance is no larger than the basic size, but is capable of being 11 microns under 10 millimeters. This brings the expected minimum to 9.989 and the maximum to 10.000 millimeters. Masumi offers a useful table to help you choose the appropriate tolerance combination in your application. If we would like this 10H6 shaft to exhibit a clearance fit, we can see each tolerance class that would satisfy this condition. Now that we're familiar with shaft selection, join us for the next episode, where we will take a look at linear shaft applications and related alterations.
And video number 4. It's the last video, and we finished our lesson. If you haven't the questions. Hole and shaft basis system.
Hole basis system. In this video, we are going to see about hole basis system. The different types of fits are obtained by associating shafts of varying limit dimensions with a single hole whose lower deviation is 0. Consider a basic hole. Clearance shaft. Clearance fit. Basic size. Clearance, 0 line. Tolerance zone of hole. Tolerance zone of shaft. When the lower deviation of the hole is 0, the minimum limit of the hole will be equal to its basic size, which is taken as the base for computing all the other limit dimensions. The limit dimensions on the hole and the shaft are computed by selecting suitable clearances and tolerances on the shaft and the hole. Interference fit. Basic size. Interference fit. Basic size, 0 line. Interference or negative clearance. Tolerance zone of shaft. Tolerance zone of hole. Forces required to insert the shaft. Shaft basis system. In this video, we are going to see about shaft basis system. In this system, the different types of fits are obtained by associating holes of varying limit dimensions with a single shaft whose upper deviation is 0. Consider a clearance hole. Basic shaft, clearance fit. Basic size, clearance, 0 line, tolerance zone of hole, tolerance zone of shaft. When the upper deviation of the shaft is 0, the maximum limit of the shaft will be equal to its basic size, which is taken as the base for computing all other limit dimensions. The limit dimensions on the hole and the shaft are computed by selecting suitable clearances and tolerances on the shaft and the hole. Interference fit, interference hole, basic shaft, forces required to insert the shaft, basic size, 0 line, interference or negative clearance, tolerance zone of shaft, tolerance zone of hole.
It was the last video. Please, if you have the questions, I can answer